of how do you come up with the tables that you see in the company database. So, so the formal design consideration, we had 3 steps. You start with a relation that has all the attributes, and then you specify the functional dependencies and multi-value dependencies. And we spoke about FDs in the last class. I'll talk about MVDs, when we get to 4th normal form. And then finally, you decompose the table into normal tables that are in normal form. And so one of the things I mentioned is that when you divide a table R into smaller tables, R1, R2, R3, and so on, if the smaller tables are in normal form, then the original table, you can get that original table back when you join the smaller tables R1, R2, R3, and so on. On the other hand, I showed you an example in the last class where if R1 and R2 are not in normal form, then when you join them, you would not get the original table. So, so that was a summary of what we did in the last class. So today so that's what we are going to be doing for the next few lectures, is that we're going to talk about the normal forms. So there are different normal forms. We have the first normal form, the second normal form, third normal form, Boyce-Codd normal form. So this one stands for the people who came up with this, Boyce and Codd. And then we have the 4th normal form. So each of these normal forms are stronger as you go up. The first normal form is, any table that you look at, we've been looking at so far, are all in first normal form. So those are tables where every attribute they're not multiple rows of attributes. So every attribute is just one value. You don't have multiple values. So these normal forms, I just want to show the relationship between these normal forms. So we have, let's see. Someone's mic is on. I don't know who it is. Okay, so so these, I just want to show that. Let me just move this down a bit. Okay, so so everything is like we started, all the tables that we are starting with, they are in kind of first normal form. So I'm going to start with the second normal form. So you have second normal form. Third normal form is stronger than second normal form. So so if a table is in third normal form, then it's also in second normal form. And then you have Boyce-Codd normal form. So if a table is in Boyce-Codd normal form, then it's in first, second, and third normal form. And then finally, you have the 4th normal form. And actually, there are more. There's also a 5th normal form, but typically people reduce their tables down to either Boyce-Codd or the 4th normal form. So, so the relationship, so like I said, the 4th normal form is the strongest one you can have. So if something is in 4th normal form, that'll imply that's in Boyce-Codd normal form. But if something is in Boyce-Codd normal form, it does not imply that it's in 4th normal form. So 4th normal form is the strongest. Similarly, if something is in Boyce-Codd normal form, it'll imply that's in 3rd normal form and 2nd normal form and so on. But 3rd normal form does not imply Boyce-Codd. So it's stronger as you go in. So I've been talking about functional dependencies in the last class. So the 2nd normal form and 3rd normal form, they don't satisfy all functional dependencies. But if you get into Boyce-Codd normal form, So Boy's core normal form is a set of relations that will satisfy all functional dependencies. And fourth normal form, they satisfy both FDs and MVDs. Okay, so in order to understand normal forms, like I mentioned in the last class, it's extremely important that you understand functional dependencies and multi-value dependencies. So even though multi-value dependencies are, like I mentioned earlier, I'm going to do that later. I just want to make sure you get functional dependencies first. So functional dependencies, they look rather simple. I showed that in the last class with some examples. For example, what is it? I think there was an example about social security number determines name. Then I think we did something. If today is a Sunday, then school is closed. So we did a few examples, that are meaningful kind of examples in the last class. So today I want to do a few more because like I mentioned, it's easy for our brains to get the logical understanding. So if I said that social security number determines name, it's kind of very easy for us to understand it, but that does not necessarily mean that if you looked at just random amounts of data, you'd be able to figure out functional dependencies. So I just want to go over functional dependencies for some examples of functional dependencies. And again, in simple form, A functionally determines B, or B is functionally determined by A, and A determines B, and the statement is equivalent to saying not B determines not A. So these two statements are equivalent to each other. So let me pick up an example from the company database. So we have D number determines the manager. So I'm going to put 3 questions down. So can 2 employees in the same department have different managers? So can 2 employees in the same department have 2 different managers? So that's the first one. And the second one is, can 2 employees in different departments have the same manager? Okay, so I would like you to look at these 2 questions and see that, so let's look at question number 1. So we are given the functional dependencies. DNO determines the manager. So what would the answer to the first question be? Yes, no, or do not, cannot know, cannot be determined by this information. So can 2 employees in the same department have different managers? So the department number is the same. Can they have different managers? So anyone, someone said no?
Yeah, no.
Yes. So yes. So when you have DNO determines the manager, and this is what I spoke about in the last class. So if you have a department number 10, then that department 10 can only map to one manager name. So the answer to this is no. Two employees in the same department cannot have different managers. So on what is the answer to the second one? Can two employees in different departments have the same manager, given this functional dependency?
Yes.
Yes. So yes, because that's that's what functional dependencies mean. So it's like saying the B is this. This is similar to the same question. Can same person manage two departments? That's the same thing. So, and the answer to that is yes, it's similar to the previous question. So, I mean, so that's the meaning of, so, I mean, so for example, if I picked up, you could have department number 1, 2, 3, and 4. You could have Smith here. You could have John here, and you could have Smith here, and you could even have Smith here. So this table satisfies the functional dependency. DNO determines the manager name. So all that to say is that if you know the department number, then you will know the department name. But given the department, if you know the department number, you will know the manager's name. But given the manager's name, you cannot know the department. So the inverse thing does not work. But the two things that work is these two. A determines B is equal to saying not B determines not A. So, or, in mathematical, if you wrote this in a mathematical term, I mean, since sometimes when you read books, so for all tuples, T1, T2, element of emp, T1 of DNO is equal to T2 of DNO will imply that T1 of manager is equal to T2 of manager. So this, what I wrote down in relational calculus, is the meaning of functional dependency. DNO determines manager. This is what it is stating, is that for two tuples, T1 and T2, if the value of DNO in row 1 is equal to the value of DNO in row 2, that will imply that the manager of D1 will be equal to manager of D2. So let's look at some examples. So okay, so let's, what is that? Okay. Okay, so we have this table. Okay, so we have this table with 3 columns, A, B, and C. So I want you to look at this table and see if you can answer the following questions. So the first one is, does A determine B? The second one is, does A determine C? And the third one is, does C determine A? Actually, let me just put that, does C determine B? And then finally, fourth, let's see, does B determine A? Does B determine C? So, so I would like you to look at this and see if you can answer these 4, or actually it's really 3 of these. So I want you to try this out. So the first one, does A determine B? Anyone? Is that true or false?
False.
Yes. Is that false? So let's see. Why did you say it was false? I'm trying to see, is A determine B? A1 goes to, yeah. Which one, which is the one that contradicts it?
A2 to B1, I believe.
A2 and B1. So we have, so let's look at this. You have A1 goes to B1. You have A2 going to, so it's, we have A2 going to B1, and we have A3 going to B1. So you think that that is not, that would make it non-functionally determined. So that's the thing, so let's look at this next previous one out here. We had department number going to manager. And so we said that here you could have Smith, 1, 3, and 4 were all going to Smith, but yet D number was. So no, if the left side, so out here, for example, so the A determines B. So we have A1 going to B1, A2 going to B1, and A3 going to B1. We do not have a case. See, so actually this is correct. It does determine, because if it does not determine, it's if you had a case where you have A1 going to B1 and you have A1 going to B2, then I would say that no, A does not determine B is wrong. I would say that. But the thing out here is that you don't have any such case. So A does functionally determine B. So does everyone, do you understand this? This is exactly similar to this case, actually. Okay, so so if you don't understand it, just ask. I'm going to do all of these anyway. I hope you had a chance to look. So does A determine C? So so we have so okay, so does anyone, would anyone want to jump in? Does A determine C, functionally determine C?
It doesn't, because A1 maps to two different C values.
Yes, you have A1 going to C1 and A1 going to C2. So you're right, it does not. So this one is wrong. It does not, functionally determine C. So let's look at the next one. C determines A. We have C1 going to A1, C2 going to A1, C3 going to A2, and C4 going. So all C1, C2, C3, C4 are unique. So therefore, you don't even have to look, because here, if you look at here, in this case, you can just look at this last column out here. Every value is unique. You have C1, you have C2, you have C3, you have C4. So on the other hand, out here, you have 2 A1s. Out here, you have 4 B1s. So, but here you have unique values. So you don't have to even look at the other columns. You can just directly say that, yes, that C functionally determines A and C functionally determines B, because every value of C is unique. In fact, when every value is unique, what do you call C actually? Do you recall we kind of have mentioned this earlier? If every value is unique, what would you call C?
A key?
Yes, it's a key. I think somebody said that. It is a key, so that's right. So is a key for the stable R, A, B, C, because it has all unique values. Okay, so this one's correct. And then the last one was So does B functionally, so B again, you don't even have to look out here, because out here, if you look at B, it's all same values, and then here they're all different values. So B definitely does not functionally determine A. And then B does not functionally determine C either. So because every value of B is exactly the same, but we have different values of A and different values of C. So it does not do that. So so do you think, I hope everyone out there, you understood the meaning, or at least in terms of this example. So in some quick ways, when you look at tables, so remember that one of the things I mentioned is that the way database designers figure out functional dependencies in tables are, one is they talk to employees, but also you have to look at the data that's already present in the organization for whom you're building a database. So you have programs, since we human beings, it's very difficult to scan through tons of data. You're writing programs also to figure out whether they functionally determine or not. There are some simple rules which are useful for us also in trying to figure out. So if you want to say, does A determine B? So let's say if there are 3 unique values for A, that will imply less than equal to 3 values for B. And if there are 3 for B, that will imply they're greater than or equal to 3 values for A. So for example, if we say that social security number and P number determine, in our works table, and suppose there were 2 values for social security number and there were 3 values for P&O. So that would mean that there would be less than equal to 6 values for R. So so you can look at tables, and sometimes instead of looking at individual data, you can just look at the count and figure out whether something functionally determines something else. Let's see. So if you go back, so if remember we started all this with this example in the previous class. So we were looking at the employee project table, and we did this division of the employee project table, and we divided into these 2 tables, and we found that R1 cross R2 was not giving you R. So this was the example that we were looking at. So for the same example, the way that you should actually divide it using functional dependencies would be, so this is the employee project example we did in the last class. So the idea is that how do you divide it? I mean, we did a wrong division in the last class. So what would be the right way to divide it? So these were the functional dependencies. We had SSN determines ename. We had P number determines P name and P location. And we had SSN P number determines R's. So the right way to really divide would be, you would have three tables. You would have R1 dash, which is SSN name, R2 dash, which is P number, P name, and P location. And then you have R3 dash, which is SSN, P number. And if you divided it, so now R1, R2, and R3 dash actually are in normal form. And I'm going to be doing all this. I just wanted to go back to that example and just show you the way to divide it. If you had divided it using functional dependencies like this, then you'd be guaranteed that R would be equal to R1 cross R2 dash. So the reason that our previous one didn't work is because we had divided it into tables that were not into normal form. So that is part of the reason. In fact, that is the reason that we're going to be studying normal forms, because we have to figure out how to divide a table into normal forms. So again, I just want to do one more example. Because we are almost at the end of class. So let's just do another example. So let's have this table with 3 rows, and then we have these values. Okay, so we have this table, and I want you to look at this table and see if you can find out, what are the functional dependencies in this table, and what is the key in this table. So these are the two things I would like you to figure out, is that, and the key. So a key is something that will determine all the other attributes in the table. So we have another couple of minutes. So just see if you can, so just start with, what about, does A determine B? So just look at all of this and see whether it's easy to see that A does not determine B, because you have A1 going to B1, A1 going to B2, and A1 going to B3. So, you can know that immediately, you can see that and say no. And the same thing when you look at B. When you look at B, the same thing is happening. You have B1 going to A1 and B1 going to A2. So. Okay, so anyway, it's 10 o'clock. I want you to look at it. So main thing on this one is, can you find the key on this one? So I'm going to continue with this in the next class. Are there any questions?